Section 14.4, Tangent Planes and Linear Approximations. Suppose the surface S has equation z equals fxy, where f has continuous first partial derivatives, and let p, x0, y0, z0 be a point on S. Then, if c1 and c2 are the curves obtained by intersecting the vertical planes y equals a constant, y0, and x equals a constant, x0, with the surface S, so that P lies on both C1 and C2, and T1 and T2 are the tangent lines to those curves, then the tangent plane to the surface S at the point P is defined to be the plane that contains both of those tangent lines. So this just seemed pretty familiar. We just slice at some constant value, and we end up with a curve parallel to the y-axis and a curve parallel to the x-axis, where we set x and y to be constants. So that's basically just where we found our partial derivatives. And then those partial derivatives were the slope of these tangent lines to those curves. So what we're saying is that you take those two tangent lines for those two partial derivatives, and you build a plane out of them. And we call that the tangent plane. So it should make sense that the equation for the tangent plane incorporates both of those partial derivatives. It takes fx evaluated at that point times x minus that x0 for that point, and fy for that point, y minus y0 for the point, and then z minus z0 for the point. So let's prove this real quick. Note that any line passing through our point has an equation of this form. So we can just divide by c to move it to the other side, and then we get c is gone on that side, and we just get a over c and b over c. However, what we can do is let a equal minus a over c and b equal minus b over c to clean up our notation a little bit. So then we move it to the other side. Because we let a equal minus a over c, a will stay positive and b will stay positive because we accommodated for that. So if this equation represents the tangent plane of P, its intersection with the tangent line, y equals constant y0, must be our tangent line, T1, because it lies inside the plane, because the plane is built from T1 and T2. So we can just let y equal that constant, and that will eliminate this. We'll get that z minus z0 is equal to a times x minus x0. So that's the equation of our tangent line T1. But the equation of the tangent line has slope fx, that's the partial derivative with respect to x, so that must be what a is. So we do the same thing, letting x equals x0 eliminates this, and it says that b must be the partial derivative with respect to y. So there we go, we've proven this. So how about we do an example where we use it? Notice this is pretty similar to when we would find equations of tangent lines. We just basically throw two tangent lines together to get the tangent plane. So how about we find the tangent plane to the elliptic paraboloid z equals 2x squared plus y squared at the point 1, 1, 3. So we'll find our partial derivative with respect to x in general, and then we'll plug in to find it at the point. So with respect to x, this is just 4x by the power rule, and this is just gone because it's a constant. So we get 4x. If we're looking at the point 1, 1, we just plug in 1, 1. So we get 4. Similarly, let's get the partial with respect to y. Notice this is 0 then, because it's constant, so we just get 2y. So we evaluate at 1, 1 again, and we get 2. Okay, so our equation is z minus our z coordinate, 3, equals our partials for our slopes, so 4 times x minus our x coordinate, 1, plus our slope, 2, times our y minus 1. So we could simplify it. If we want to get z by itself, we just get z equals 4x plus 2y minus 3. Similar to the way that we used linearization in single variable calculus, we can use linearization in multivariable calculus to approximate the value of a function. So in this case, we just take our equation of our tangent plane. Remember, we had z minus z naught on the left. So we basically just take z naught, move it to the other side. That's the function evaluated at the point AB. We just have z left, so we can rename z into L as a function of x and y, and we get this equation over here. And if we want, we could use this to approximate the value of the function, f of x, y. It's called the linear approximation or tangent line approximation of f at AB. Next, suppose z equals f of x, y is a function of two variables where x changes from a to a plus delta x and y changes from b to b plus delta y. So delta x is the change in x, delta y is the change in y. We call those the increments, as we've seen before. So then the increment of z is delta z. So that's just f of a plus delta x, b plus delta y, minus f of ab. That should seem familiar because the increments in single variable calculus, when we just changed delta x and then we had the corresponding delta y was a function of the change in x. So for example, if we went from 0 to 2, we might look at delta x as 2 minus 0, and then we might look at delta y, the change in y, as, let's say, f of 2 minus f of 0. So that's basically what we're saying over here. We change from a to a plus delta x, so that's our 0 and our 2 basically, but it's multivariable, so we also change from b to b plus delta y. So that goes in our numerator also. This was just if we wanted delta y divided by delta x. So that's where we have delta y over delta x, and remember that's the slope of the secant line. That's just literally change in y over change in x. Remember we said that the derivative is the limit of the slopes of the secant lines. So that means that delta y over delta x is approximately dy dx. So I could write this, for example, dy dx is approximately delta y over delta x. So if I wanted to actually set it equal, it's just basically equal, and it's off by like some constant, say. So I could set it equal if I just added whatever's missing. Let's call it epsilon, that constant. So then if I wanted to get our increment delta y by itself, what I could do is I could set delta y equal to dy dx times delta x plus that constant times delta x. Instead of writing dy dx, if I wanted, I could even just write the derivative in terms of prime notation. So it is f prime of x, and I do this just by multiplying through by delta x. So notice this kind of relies on this epsilon term tending to 0, because if I take the limit of this thing, and I take the limit of this thing, then I should get that the limit of this thing becomes this thing, so this thing must go to 0. Maybe it makes a little more sense if I subtract epsilon, then the limit of this should equal dy dx. So this works provided that epsilon tends to 0. The difference between dy dx and whatever number I'm adding to accommodate for the difference between that and our increments just goes to nothing as we take our limit. So if our function is differentiable, this must be true where epsilon goes to 0. And an analogous form for multivariable calculus is with our increment delta z in terms of our partial derivatives instead of our f prime. So in that case, we have two constants we have to add to accommodate, because we need one to multiply by delta x and we need one to multiply by delta y. So both of those must tend to 0, as our change in x and change of y tends to 0. So if the partial derivatives fx and fy exist near AB, and are continuous at AB, then f is differentiable at AB, using this definition of differentiability. Okay, how about we show that xe to the xy is differentiable at 1, 0, and find its linearization there. Then we can use it to approximate f of 1.1 minus 0.1. So we'll write fx of xy is equal to e to the xy plus xy e to the xy, because we just use a product rule. And derivative of this guy is 1, we keep that, and then we keep this without the derivative, take this with the derivative, and y is a constant, so it hops out. Okay, let's plug in 0, 1 now. We get 1, because 0 kills that guy off, and then e to the 0 is 1. Let's get the partial with respect to y. So with respect to y, this is not the product rule anymore, because everything's constant except for y. So x is constant, I just have that hop out. So I get x squared e to the xy. So again, plugging in 0, 1 just gives me 1. So let's look at the linearization. Well, that would be f of 1, 0 plus fx of 1, 0 times x minus 1 plus fy of 1, 0 times y minus 0. Okay, so this is just 1 plus 1 times x minus 1 plus 1 times y, and that equals x plus y. So first we showed that our function was differentiable by using this theorem over here and seeing that our partial derivatives fx and fy exist and are continuous. And now we've found the linearization. So last thing we have to do is use it to approximate f of 1.1. So due to our linearization, we're saying that xe to the xy is approximately our linearization x plus y. So that means that f of 1.1 minus 0.1 is approximately 1.1 minus 0.1, which is 1. And this is actually kind of cool, because if we look at the actual value of f of 1.1 minus 0.1, let's say using a calculator, then we get that's 1.1 e to the minus 0.11, which is approximately 0.98542. But look at that linearization. We literally just added our x and y coordinates, and we got very, very close to taking some decimal and multiplying by e to some negative decimal power, and it's like a mess, but it was so little work to get so close. On a hot day, extreme humidity makes us think the temperature is higher than it really is, whereas in very dry air we perceive the temperature to be lower than the thermometer indicates. The National Weather Service divides the heat index, also called the temperature humidity index or humidex in some countries, to describe the combined effects of temperature and humidity. The heat index I is the perceived air temperature when the actual temperature is T and the relative humidity is H. So I is a function of T and H, and we can write I equals F of TH. The following table of values of I is an excerpt from a table compiled by the National Weather Service. Let's find a linear approximation for the heat index I, where T is near 96 degrees Fahrenheit and H is near 70%. We'll use it to estimate the heat index when the temperature is 97 degrees and the relative humidity is 72%. So in order to do that, we need our partial derivatives with respect to T and H. So how about we approximate Ft first? So let's look at an approximation for ft of 9670. Well, if I look at 9670, that's right over here. Obviously, this is the value of f of 9670, not the partial derivative. So in order to get the partial derivative, we need slopes. We need slope of tangent line, which we can't really get from a table, but we could take secant slopes, and we can use those to approximate tangent lines, just like we did in single variable calculus. So how about we get the secant for nearby? How about we do 98 to 96, where 70 is held constant the entire time. So that'll be our partial derivative there. So let's look at from 96 to 98 and 125 to 133. So we could say that our partial is approximately f of 9870 minus f of 9670 over 98 minus 96. That's the slope of the secant line there. So that's 133 minus 125 over 2, which is 4. However, it would probably be good for me to go the other direction also. I went a little bit above my value. How would I go a little bit below? So let's look at 94 to 96. So let's look at ft in that case. Maybe I'll go over here for more space. So ft of 9670 is also approximately f of 9470 minus, what is it, f of 9670 over 94 minus 96. So that's 118 minus 125 over minus 2, and the minuses cancel and just leave us with 3.5. So if I went a little bit below, the slope of the secant line was 3.5, a little bit above was 4, so we could approximate the slope of the tangent line using the average of those two. So how about we say it's 3.75? So I'll say that our partial derivative at 9670 is about the average of 4 and 3.5, which is 3.75. We'll do the same thing for the partial with respect to h. So here's 9670 again, but this time I'm going to keep 96 constant, because I'll keep temperature constant, and I'll just vary h. So I go a little bit above, so I look at from 125 to 130. So I do f of those values, subtract, divide by 5 this time because I'm, increasing by 5. And then I do the same thing and I go from 121 to 125 and divide by 5. So this gives me 5 over 5, which is 1. And over here, this gives me negative 4 over negative 5, which is 0.9. 0.8. And then the average of 0.8 and 1 is 0.9. So I'll say that the partial with respect to h of 9670 is approximately the average of 1 and 0.8, which is 0.9. Okay, so now I got my partial derivatives. I can write my linearization. So I'll say that f of th is approximately f of 9670 plus our partial with respect to t at 9670 times t minus 96 plus our partial with respect to h at 9670 times h minus 70. Okay, so that's approximately 125 plus 3.75 times t minus 96 plus 0.9 times h minus 70. So we get f of 9772 is about 125 plus 3.75 times 1 plus 0.9 times 2, which is 130.55. So to answer this question, we see that our index I, our heat index I, is about 131 degrees Fahrenheit when our temperature is 97 degrees Fahrenheit and our humidity is at 72%. For a differentiable function of two variables, z equals f of xy, we define the differentials dx and dy to be independent variables. That is, they can be given any values. And the differential dz, also called the total differential, is defined using the partial derivatives dx and dy. This is pretty similar to the way we defined in single variable calculus dy equals f prime of x dx. So in general, because dx can take any value, it's an independent variable, we would just set dx equal delta x, and then we would see what the corresponding dy would be and use that to approximate delta y. So in this case, we have two partial derivatives. We have got two independent variables, so we'll set dx to be delta x, we'll set dy to be delta y, and then we'll see what the corresponding dz is and use that to approximate delta z. So as an example, let's find the differential for this function right over here. So dz is equal to our partials with respect to x and with respect to y times dx and times dy. So we get that that's just, well, let's see, that's just going to be 2x, and this is just going to be 3y. This is constant, so it's 0. And then we've got 3x again. Well, not 3x again. I mean, we had 2x before, so now it's just 3x. And we have, because that's from over here, minus 2y, and this was 0. Okay, what if x changes from 2 to 2.05 and y changes from 3 to 2.96? Let's compare the values of delta z and dz. So we have x equals 2. We're going to set dx to be delta x because it's an independent variable. So that's just 0.05. We'll set y equal 3 and dy equal to delta y equal to negative 0.04. Because this changed by 0.05 and this changed by negative 0.04. So then our dz is 2 times 2 plus 3 times 3 times 0.05 just by plugging in, and then plug in for the second part, and we get 3 times 2 minus 2 times 3 times negative 0.04. So it just works out to 0.65. It's actually not that bad. You could even do this. I mean, it wouldn't be fun, but you could even technically do it without a calculator because you would just be multiplying a little bit and adding. Whereas on the other hand, let's get delta z. So our increment instead of our differential. So that's f of 2.05, 2.96 minus f of 2.3. It's our change in z. So that's just 2.05 squared plus 3 times 2.05 times 2.96 minus 2.96 squared minus 2 squared plus 3 times 2 times 3 minus 3 squared So that you probably do want to use a calculator for. It's a lot more work with the squares and everything else. Maybe you could do it by hand too, but take a little bit longer. You should get 0.6449. So 0.65 versus 0.6449. They're very similar, but this was way easier to compute. So that's why we usually use differentials to approximate increments. So let's take a look at this example. We have the base radius and height of a right circular cone measured to be 10 centimeters and 25 centimeters, respectively. There's a possible error in measurement of as much as 0.1 centimeters in each. Let's use differentials to estimate the maximum error in the calculated volume of the cone. So the volume of a cone, remember, is pi r squared times the height divided by 3. So our differential dv is the partial of v with respect to r, dr, plus the partial of v with respect to height, h, dh. So that's 2 pi r h over 3, holding h constant. And holding r constant, we get pi r squared over 3 dh. So we'll take, let's see, our possible error measurement is at most 0.1 centimeters. So that means that we'll take, we've been given basically delta r is less than or equal to 0.1, and the change in h is also less than or equal to 0.1. I'm taking the absolute values just in case either of these are negative. And we need to choose values for dr and dh, so let's set them equal to delta r and delta h. We'll take dr equal to 0.1. We'll take dh equal to 0.1. And we're given r is 10 and h is 25. So we have everything we need to plug in. We'll get that dv is 500 pi over 3 times 0.1 plus 100 pi over 3 times 0.1, which is 20 pi. So in conclusion, our max error in our measurement is about 20 pi cubic centimeters, which is about 63 cubic centimeters. Just like the way that we extended single variable linear approximations, differentials, and differentiability, we can do pretty much the same thing for further variables, higher dimensions. So if we want to do it for 3 variables, we just add another partial derivative times the next variable minus the next point we're at, coordinate of the point we're at. So in this case, we'd have a 4th variable over here. You could call it w if you want. So if w equals f of x, y, z, then the change in w is the change in your w value, or your new w value minus your original w value, and your differential is defined pretty much the same way also in terms of partial derivatives and the independent variable differentials. So let's use this to find the largest possible error in the calculation of the volume of a box, where the dimensions of the box were measured to be 75 centimeters, 60 centimeters, and 40 centimeters, where each measurement is correct to within 0.2 centimeters. So the volume of a box is v equals length times width times height, so let's say x times y times z. So our differential dv is the partial of v with respect to x dx plus the partial of v with respect to y dy plus the partial of v with respect to z dz. Oops, I just wrote dy twice. Okay, so let's look at that first partial with respect to x. These guys are the constants, so we get yz dx plus xz dy plus xy dz. Okay, so our delta x we said is less than or equal to 0.2 in this case. And all of our measurements are actually, so delta y is also less than or equal to 0.2, and delta z is less than or equal to 0.2. All of our errors and measurements are within 0.2. Okay, so we'll choose dx to be 0.2, dy to be 0.2, dz to be 0.2, and we're given that x is 75, y is 60, and z is 40. So our increment delta v is approximately dv. So our change in error delta v is approximately our differential dv, and that's 60 times 40 times 0.2 plus 75 times 40 times 0.2 plus 75 times 60 times 0.2, which is 1980 cubic centimeters. So that's actually pretty interesting. That means that even with an error of just 0.2 in our measurements, we ended up with an error in the volume of almost 2,000 cubic centimeters, which seems huge, except that the box is actually much bigger than it seems. If you multiply length times width times height, then you would see that this is only about 1% of the entire volume of the box. So it's actually not that big of an error.